In this segment, we're going to take a look at results along strips relative to the post-tensioning that we have modeled in the slab. And one item that we didn't do in the last segment, but I'll bring it up here, is we may wish to add, some PT along these two edges, so we have some continuity and pre-compression along that edge, and instead of having just this hard line of tendons, being stressed in this direction, where we have this corner, we could develop cracking here. So we may want to have some continuity tendons through that location. We didn't add them. We're not going to add them, but just wanted to make sure we make a comment related to that. We're now going to analyze the structure. So we've defined our load combinations. We've defined our strips. We've input our tendons. We now want to check pre-compression, stresses, balance loading. We're not going to go through each and every problem region within the slab, but we're going to pick one support line and take a look at that particular support line and just make some general comments about the results for the design. And we'll show also the use of the optimizer in this segment. So I'll go now to analysis. We've already meshed the slab in a previous segment, but I'll remesh the slab so we can see that here. We'll use a simplified with default settings for meshing. We're going to save and mesh the slab. And you can notice that the program says there's tendons that are outside of the slab. Well, the tendons, when we map these four strips, the support lines may not have been exactly perpendicular to the edge of slab, so one of the tendons is outside, one of them is not. It's easy enough to modify that. If we just select the tendons under the tendon toolbar, we can trim and extend the tendon, and that will resolve that. If there's so much of a slab or a tendon end that's outside or inside of the slab, for example, if this is way out here and I wanted to trim it, it's not going to trim unless our tolerance exceeds that distance. So I can always change the tolerance here. If I change this to 7 feet, and then I try to trim that, that still may be more than 7. If I drag this down some and try to trim extend, again, that still may be more than 7. So just make sure that you set the tolerance to a proper distance. I don't know how far this is out, but I can just go back and set that back manually if needed. So we'll go do that like so. Having done that, we should now be able to go back to analysis and mesh the slab. Okay, once the slab has been meshed, we're going to execute the analysis. So we'll do a linear elastic analysis here. We're going to select execute, and we're going to generate a solution for all of the combinations, including the cracking. We have to select the cracking first in the linear elastic in order to be able to produce a crack deflection result later on. So we'll select all combos. The default usage case, or let's say stiffness profile of the slab, is uncracked, meaning we haven't assigned any stiffness modifiers to any of the components. We'll say OK, and we'll produce this first solution. We'll select yes to save the solution, and the result display settings dialog will appear. So initially we looked at the deflection under self-weight only, and it was roughly 3/4 of an inch. That was without any post-tensioning. If we just take a quick look at the deflection under service total load with PT and with loading, we might be able to estimate where we end up in terms of long-term deflection just by using a kind of a gross multiplier. And you can see that the max deflection is still out in this region. We're going to ignore that region. We might this is kind of part of the core. We might add some PT along this beam just to control that deflection. So we're mainly concerned about the deflection outside of that core region. And we can see that the deflection along this contour line here on the inner zone of this region where we have the one-way slab transitioning into more of a two-way slab is roughly 0.63 inches. So assuming that our multiplier is, let's say, 3, we have a total long-term cracked deflection of 1.8 inches, maybe plus minus. So if we then evaluate that against our criteria for total deflection or for live load deflection or whatever the deflection evaluation is, we can determine whether or not we might need more PT initially or not. So those are just some things we can do with the initial analysis results that that are produced once we run the analysis. The second step, in order for us to gather information on stresses, precompression, and balanced loading, is to design the strips. So we'll go now to floor design. We've already produced the section cuts. I'll produce them again just to show the step. So we'll generate the section cuts, and that will produce all of the design cuts along each of the support lines. Okay, so we have our design cuts shown. The screen is getting a little bit congested with information. I'll go back to result display settings, and I'm going to just go ahead and clear that contour that we had. I'm also going to turn off our finite element mesh. So I'll go to model, we'll go to analysis, and under visibility we'll turn off shell elements. We're also going to turn off the tendons. So I'll go to tendon and turn off by toggling show display tendons, show hide tendons. Okay, we have our section cuts now with support lines in the X and Y directions. Back in floor design, we're going to design the sections. So we've produced them, now we're going to design them. And this will not only give us stress checks, both for precompressive, centroidal stress, extreme fiber stress, flexural stresses. It will also give us a view of reinforcement for the design cuts, balanced loading, moment capacity, and different graphical checks that might be applicable to the design. We'll select yes to save the results for the design strip. Another way to check deflections based on the linear elastic solution, not the crack solution, would be to use the red eyeglasses again. So once the section design is done, we're going to navigate down to design sections. And that's shown here. I'll go ahead and mark that. So we're kind of focusing on this block of graphical result settings. We're going to use result display settings too. We might come over here and use settings as well to alter the size of text and so on. So using this option, we have this deformation option. Okay, and based on the combination that is selected, for example, service total, if I go ahead and select the option for Z deflection, the program will generate a span deflection ratio for each of the spans along the support line. So for example, if we look at these spans in this direction, kind of this one-way direction where we have the maximum deflection, we can see, and I'll go ahead and turn off the X direction, we can see that the maximum deflection at any point along this curve is 0.75. The program takes the distance between these 2 points, here and here, and it takes that distance divided by the maximum within that distance on any section cut to produce this result here, and that's for the combination selected. This is not applicable to the crack deflection check. You have to use contours to check crack deflection, but it is applicable to the linear elastic solutions for any of the combinations that have been created. Now, along the strips, we're going to primarily focus on results using these settings under floor design. We're in the floor design ribbon strip results panel. And if I want to show the graphical result on any of the design cuts, I can turn on this numerical display option that shows me the integrated design deflection along the strip cut, along the section cut for any of the different strips. It could be in the X or the Y. If I wanted to switch to the X direction, I can turn off Y, I can go to X. And you can see these values are much smaller because we have beams and a lot of PT within those beams. So there's no real issue there for the X direction. It's mainly controlled by the Y. Now, if I wanted to change the threshold for which the check is made graphically, I can always go to Result Display Settings. Here, the deflection maximum allowable ratio is 360. If I was to change that to 700, for example, and I apply, the program will show where this fails. This is L over 657, which is doesn't meet this particular target, and we get this failure here at this particular location. So this controls a graphical check. I'll go back to 360, something more appropriate, and that updates the graphical check. So that's deflection. For any PT design, we need to make sure we have enough pre-compression for the strips. And so going back to the Analysis tab, I'm going to turn on the option for pre-compression. And we're going to use pre-compression number of tendons first. Let's go ahead and make sure this stops blinking. We're going to use pre-compression number of tendons, which really takes the total number of tendons times their force divided by the area of the section. And you can see there's a couple of locations where we have insufficient pre-compression. Those are marked by pink. And the Result Display Settings is currently set to 125. So the program is checking against 125. And if we zoom in and take a look at these results, we can also go to Settings, change the number of significant digits to 1. I'll change the font height here to 12 and apply. We're really close to 125. If we round up, we're at 125. So, we might say, well, I'm going to go down to 124, for example, and apply that. We can see where we're less than that threshold. So it happens mainly where we have a drop panel. If we have to bump up the amount of pre-compression through the drop panel, then we're going to have to increase the number of tendons passing through this location. We could do an add tendon that starts, for example, here, and run that out to feed that zone with more pre-compression. That's one way to resolve that. But we need to resolve any pre-compressive issues before we check stress. That might be just a natural progression in the design. We're plenty good with pre-compression on these interior zones. We have roughly 300 psi in pre-compression there. And then that also may be predicated by the presence of the beam. If you recall, we had that issue on these tendons when we first mapped them. Well, we didn't go back and check, but we had a fairly tight distribution of cables along these strips here. And again, that may be due to the presence of the beam. So something that we may want to go back and check if we were to carry through with this design. Over on the opposite end, again, we have the need maybe for a little bit more pre-compression here. So again, we could add an add tendon anchor here, or just increase the number of tendons through all spans in this zone. If we increase the number of tendons, we need to calculate how many more tendons we need to provide enough pre-compression through the drop cap. That would be predicated by the area through that cap at the maximum width. So it'd probably be this section right here, where we have the lowest, the lowest value, which is 92.5. Let's go ahead and turn the tendons on. Okay, so currently we have 92.5 psi of precompression through that zone, and then 105.7. If we take the area here, and the area is 4660, so we're going to take 4660 times 150. Okay, that's 700 kips. We know we already have 16, so we'll take 700 minus 16 times 27, so 16 times 27 is 432 kips. So 700 minus 432 is 268, divide by 27. We need an additional 5 strands in these zones. So we would have to go from, let's see, 8 to 12 or 13 tendons in these two lines, or add an additional tendon with 10 strands as an add tendon to meet the precompressive requirement in just those drop panel areas. And based on interpretation of code, and especially the 318.14 ACI code, for example, you require enough precompression to meet the allowable minimum for every section along a strip. So technically, you would need to meet the precompression over the drops based on that interpretation. But that's left to the judgment of the engineer performing the design. In the other direction, we'll go ahead and switch this. I'll turn off the tendons. I'll go back to floor design, and I'm going to switch this to this direction. You can see we have a little drop in precompression again over these zones here where we have the drop cap. So it goes from 159 down to 111. Here it's at 80. Why is it at 80? Well, this strip or this section cut kind of cuts through this entire slab along that length, and if you double click on it, you can see it's actually picking up part of a beam. So that's all included in the section, and the post-tensioning in that region, we only have probably this tendon passing through the section cut, not this tendon. If we double click, we can confirm that. If we double click here, you can see we only have one tendon passing through, which is this tendon here. So we get a drop in precompression. We can either solve it by readjusting the section cut or the strip, or by just moving this tendon into this zone so that we feed that area with precompression. One or the other. Physically, whether or not that's possible, that's another story, but from a modeling standpoint, we have to adjust it based on what we believe will be the physical makeup and the physical characteristic of the particular location and situation. On the opposite end, we have a cut here, and in this case we actually have two tendons. You can see there's a tendon here and what appears to be a tendon here. So there are more tendons in that region, and then we have a small uptick in force. If we double click on this, this is 15 strands, and this is 12. We may not have a balanced number of strands on either side. Let's take a look. Yeah, this is only 8 strands, so this here we might have to maybe change also to 12. And this we could actually reduce from 15 to 12, 10 or 12 I would say. So we'll do 12 again. And we would need to rerun based on that modification. Okay, so that's the precompression. If we check precompression based on FEM, this is really the axial force divided by the area of the section. So you might see variance in the curve because this means that any axial restraint in the plane of the slab is considered when we calculate the axial force in the section. So if you have fixed supports, if you have fixity between walls and slabs, this can affect the in-plane the ability for the slab to shorten in plane in reality in the direction of the tendons. And whether or not that actually mimics real life condition based on your detailing depends on what the outcome what was produced in terms of the outcome. So if you're going to use this FEM option, you need to make sure that the walls to slab connections, the support conditions allow for the slab to shorten freely so that it mimics, again, real life conditions for the transfer condition of the force into the slab for the PT. A lot of times you're going to use this number of tendons option just as a bypass, knowing that you're going to detail it, allowing it to shorten freely. So that's what the two different options are. For stresses, let me turn the tendons off. For stress, we're going to check, for example, the top stress and the bottom stress. And you can see it says no good, but on screen, everything in the X direction is okay. And we mentioned that we have quite a bit of tendons and a lot of drape in the beams. So if I, for example, look at the bottom stress, you can see at the beam locations we still have compression on the bottom fiber, which means that we probably have overbalancing for these spans. If I go to balance loading, you can see this is 141, 152, 189. We just have too much drape for these spans. So we might have to go back and adjust the drape and start raising that vertically so that we can control this load balancing. It's not as drastic once you get on in the interior here, plus these spans are just shorter than the one-way span in the Y direction. So if we look at the bottom stress again, for these spans, these are in compression on the bottom. These are actually slightly in tension, so you get less load balancing there percentage-wise compared to the beams, 152 versus 95, 69, and so on. And then when you move down towards this beam, again, if we look at the bottom stress under service total, we have compression on the top. It's not as severe as the beams on the top. So the adjustments that might be made here would be wherever you have a load balancing issue, we're going to adjust the drape, and we have enough room to adjust the drape because we have so much overbalancing of the PT in those beam locations that we have the room to adjust and move the drape vertically. In the other direction, I'll go back to floor design and just turn on the Y direction. This direction is actually being checked where we exceed the allowable stresses. The slab, in this case, we didn't change the criteria, so we never made a setting change to the strength of the slab. This is 4,000 psi concrete, and if we double click on the slab, you can see this is concrete 1 under criteria. Concrete 1 is 4,000 psi. The code that we're using, let me go back to design code, is ACI 2011, and the allowable stresses are set to 6 square root of F prime C for two-way slabs, for beams 7.5, and for one-way slabs 7.5. So here we have two-way slabs which are being checked. Here we have one-way slabs criteria being checked, and again two-way slab. And at the bottom fiber you can see these actually exceed the target, and the target here is 379. You can see that number right there. The target here is, for example, 474, and you can see those targets here where they're exceeded, 474.3 versus 548. So in this case, we already have maxed out drape. The only answer would be to either increase the thickness of the slab, increase the strength of the slab potentially, or we could adjust the number of strands. We might have to add more tendons to these banded lines. Naturally, we said earlier that we're going to increase the number of tendons for precompression. So that gives good cause to check precompression first and then go into checking stresses, because the outcome of having changed for precompression would have been something closer to normal or closer to the target for the stress check. And so we have a bottom failure in flexure here in tension, for stress, and then at the top we have some overstress here near the supports at the top, especially along this edge here and along the bottom shown here. Okay, and so we're going to, in the next segment, we're going to use the optimizer to show how to optimize these cables in a couple of these locations for producing a result that meets the allowable stress. Again, we might check balance loading in this direction. So we have, load balancing in this span here is high. We have the ability to drop the drape in the mid-span, meaning raise the profile from the bottom up. And if we look at the stress check here, again, we're kind of hovering near neutral, where we're just slightly in tension. So we have the ability to move that tendon up and not really cause a problem there from the stress standpoint. Same thing in this region here. Going back to balancing, we do have an overbalance here, but we also have a situation where we have too much tensile stress. So we can't move the cable up to compensate for balancing, otherwise our stress would increase. This is a case where the outcome of the design might be such that the load balancing maximum value that we've targeted is exceeded, and that would lead us into checking the deflection under sustained loads or under service level load conditions to make sure we don't have any crowning in the slab. So load balancing technically is not a requirement per code. It's a design tool, and we have to be careful when we exceed that value so that we don't have deflection upward in the slab. Okay, so that's all part of the balancing act when we're designing the slab for the PT. Okay, so in the next tutorial we're going to talk about the ability to use the optimizer to kind of fix some of these issues that come up in the course of the design. But additionally to the design of strips, we can also check reinforcement and capacity of the section. So we're just going to assume in this case that the design is sufficient, and even though we have a few tweaks to make to actually satisfy those requirements, we can generate both reinforcement and then look at capacities of sections for the design. If we go to floor design, I'm going to select calculate rebar plan for the envelope. If I select OK, the program will produce reinforcement in the top and the bottom for our design along our strips. So you can see the green reinforcement is top rebar, bottom reinforcement is red, and then the blue reinforcement indicates that the rebar passes through locations where we have two different depths or two different section depths. So it's just an indication to the user to be careful in terms of detailing that reinforcement. If we go to rebar, under the display option, let me turn off the design strips, and I'll go over here to reinforcement, display manager. We can then display, for example, if I want to look at just bottom bars in the slab, these belong essentially to the strip. So we have bars here that are shown as distributed. This is for like a one-way slab or even a two-way slab. You can see the two-way is actually shown as grouped. The one-way is shown as distributed, and then the beam rebar is also shown as grouped. This is located down in the beam. So the user can manipulate the rebar on screen. You have the ability to move the rebar, change the size of the rebar, the number of bars. You can control the display of the bars using the display manager. Here we're looking at the top bars in the, we're looking at, let's see, yeah, the top and the bottom bars, bottom in the Y, top in the X. So if I do top in the X and Y, we have something like this. We can export the rebar to a CAD file. So here we can set up the different export settings for reinforcement, the appearance, the font size, the font type, symbol size, circle size. We set that up, and then we can go to File, and we can export out that drawing as a DWG DXF, and that allows us then to take that and convert it into a construction document potentially, or if it's Revit, we can always import the rebar back into Revit using the Adapt 2018 or 2019 Revit link. Okay, so we'll go back to our default display. I'll go back to floor design. I'm going to turn on the strips in the Y direction. And one thing we can also do is check moment capacity with demand. So for all of our design cuts, the green represents the positive capacity curve, the blue represents negative capacity, the gray represents the enveloped strength moment for our ultimate factored moment for the design cut. So if we double click, for example, at this location we have 0 reserve capacity. The DCR is 1 and 1 and 0.9, 0.4. Here we have a little reserve where you get to the inflection point and you get back to a location where there's 0 reserve. But if I double click on any section cut, I can use the support line design sections dialog to review results. Here we have a physical representation of the cut, a representation of what rebar is required in addition to what's already in the cut, and the program itemizes that rebar in this form in a textual format. Here we need 3.1 square inches, which is governed by strength, and then it gives an accounting of the criteria, moment capacities and demands for positive and negative moment, and also if it's a one-way slab or beam, it will give a shear VU over phi-VC ratio for that cut. So this gives us more information for the design cut in question, which is at a specific location within the slab. That will conclude this video tutorial. Look for the next video tutorial, which will discuss the optimizer in being able to solve tendon overstress problems, precompressive problems, or balance loading problems. Thank you.